In this video, we're going to look at the second half of the page on information about extreme values from our section 3.1, 3.2. So we're going to look at two different tests for determining maximum and minimum of our graphs. First, let's look at the first derivative test. So in the first derivative test, suppose C is a critical number of a continuous function f that is differentiable near C, except possibly at C itself, because as we learned in the previous video, critical means that the derivative might not exist. So let's consider the situation if f prime, the derivative, changes from positive to negative at C. So we can draw a little image of ourselves. Here's C. If our graph changes, so the derivative is positive and then negative at C, what do you suppose our graph has at this point C? So we know f prime of C is either 0 or DNE. Well, if the derivative is positive on the right and negative, or positive on the left, negative on the right, that is changes from positive to negative at C, then f must have a local max at C, because our graph is then increasing to the left, decreasing on the right. So we have a local max. And now in the opposite direction, if f prime changes from negative to positive at C, so we have down, negative to the left, positive on the right, then we must have a local min. Now we don't know if we have a global max or min at C. We only know that near C, we have a max or a min, or rather at C, we have a max or a min that's just local, just near that value. Then we know if f prime does not change signs at C, so maybe it's positive, and then it's continuing to be positive, or vice versa. At C, if we go decreasing, decreasing, then we know that f has no local max or min at C. So that was the first derivative test. We can also determine local max and mins based on the second derivative test. So let's just recall some things that we know about the second derivative. So we know if the second derivative is positive, then we have a function that's concave up. If the second derivative is negative, then we have a function that's concave down. So from this, we can determine whether or not we have a max or a min at the center point, at the value of C that we've identified as the critical value. So if the derivative at C is 0, so we know we have a horizontal tangent line there, and the second derivative is positive, well, then we know we have concave up, which means we have a minimum. So if that is the case, we know we have a local min. If the derivative is 0 at C, so we know we have a horizontal tangent line, and the second derivative is negative, which means we have concave down graph, then we know we have a local max. So one thing I will say is that it's tempting to try to memorize these relationships. Memorize meaning identify here. Okay, if we have changes from positive to negative, then I need to memorize that's a local max. What's more important is just to be able to think through what's going on in the situation given. So I encourage you to take some time and just meditate and sit and let your brain steep on these ideas rather than force your brain to memorize some relationship. But now let's finish off this page with one very important final rule. So a general rule to find the absolute max and minimum. So far, we've just looked at local of a continuous function on a closed interval. What does that mean? That means an interval that contains its endpoints. So for that preliminary example, that graph or function was located on a closed interval because it included midnight all the way to hour 21. And our graph was something like, okay. What we do is we compare the output values of the function at the following locations: at the critical values of f and at the endpoints of F. And rather not of F, but endpoints of F, yeah, on the interval. So to finish up here, let's just look at an example for finding absolute max and mins. So we find absolute max and mins on a closed interval, or if we're given a closed interval. So here's like our inputs. Suppose our graph looks like this. Similar to that tide problem, maybe. So now where would the critical points of our function be? Have a critical point here, here, and here. And then we have our endpoints here and here. So then to determine where we have global max and mins, we need to check the output values for all of these red dots. So in looking at this, we can see that our absolute largest value happens here at this input here, and our absolute minimum happens here at the endpoint. So notice the critical value, or rather the endpoint, is not a critical value because we don't have a derivative of 0 here, but we do have a global min because our graph is lowest at that point. It's lowest across this whole curve at that point. Awesome. All right. Thanks for watching. Please rewatch any parts of this video to help this material become more familiar.